mechanical vibrations due to damped vibrations, undamped vibrations, okay, free damped vibrations and free undamped vibrations. Then the same things but with forced vibrations. So we have analyzed the vibrations, particularly with and without damper, okay, um, free vibrations and forced vibrations. And we have also seen that the force vibrations can be caused by the ground movement or by caused by the unbalanced mass. Okay, all those cases we have seen. But so far we have been talking about the single degree freedom vibrations. Okay, so only single degree of freedom. So now in this session and next session, we talk about the multi degree of freedom. So when we deal with multi-degrees of freedom, the analysis goes in the same way. So that means first we need to derive the equations of motion, then we need to solve the equations, or in other words, we need to get the expressions for the response of the system. Okay, so the difference is in the past we used to have only one equation of motion. Okay, we were dealing with only one variable. Okay. So now in multi-degrees of freedom, so you may have two variables or you may have three variables or you can have any number of variables. So degree of freedom refers to the number of coordinates required to completely describe a system. So the number of coordinates required to completely describe a system. So now if you see here, okay, focus here on this. So this is a 2-degree freedom system because there are two masses. So these two masses will have displacements x1 and x2. Okay, and if you want to describe the motion of this system, then you need to have an equation of motion for mass 1 and also an equation of motion for mass 2. So there are two equations of motion required. Okay, um, there when we write the equations of motion will be in terms of the forces acting on m1 and again another one in terms of the forces acting on mass 2. So we need to derive two equations of motion. So that is because this is a 2-degree freedom system. All right, so then we'll see another example here, the automobile suspension system you can see here. Okay, so if you see the free body diagram acting on this automobile, okay, so as the system moves, because there's a springs at the front and at the rear of the automobile. So these two are the suspension systems. So due to the suspension systems and due to the movement, okay, there could be two types of displacements. One is the pitch, which we measure in terms of angular displacement, theta. The other one will be the bounce, the vertical motion. So we can describe in terms of the vertical displacement. So if you want to describe the motion of this system, okay, you can see here the free body diagram. Okay, so there are two types of displacements. One is the angular displacement theta, so which is the pitch of the automobile or the suspension system, and the other one is the vertical displacement, so which is the bounce of the system. Okay, so there are two coordinates are required, and thus this system requires 2 degrees of 2 equations of motion. And the analysis also should be done for two systems. All right, so you can see another example here. So this is a double pendulum system. So here you can see, so there are two masses attached and the two card lengths. So there are two masses, M1 here and M2 here. And M1 is attached to L1 and M2 is attached to M at a length of L2. Okay, so we can describe here the motion of this in terms of uh, linear displacements x1 and x2. So x1 and x2 will be the linear displacements of mass 1 and mass 2. So then we can also describe this system in terms of the angular displacements theta 1 and theta 2. So essentially, this is a 2-degree freedom system. Okay? So there will be two equations of motion for this, and also there will be two frequencies for this system. And we need to find solutions for both in terms of the displacement x1 or the angular displacement theta 1 and displacement x2 or the angular displacement theta 2. Okay, so these systems are different compared to the systems, single degree freedom systems, which we have been discussing in the last 4 sessions. Okay, so let us look at this particular system here. Okay, focus on this. Okay, so focus here. This is a 2-degree freedom system because there are two masses, M1 and M2. So M1 will have a displacement x1, which is a function of time t. Okay, so the displacement of M2 is x2. Okay, again a function of time. So there's a force F1 acting on M1, mass 1, and there's a force F2 acting on mass 2. So you can see there are three stiffness, M1, M2 are connected with three springs, okay, K1, K2, K3. And also there are three dampers, C1, C2, C3. So we only consider the viscous damping. That means we ignore the frictional effects acting on the system. Okay, so now for a system like this, we need to draw the free body diagram to derive the equations of motion. So the free body diagram for both the masses are shown here. Okay, so you can see the free body diagram for mass 1 and a free body diagram for the mass 2. So we apply the Newton's third law, so which is the net force acting on the system we equate with the mass into acceleration. So what is the force acting on the mass M1 and what are the counteracting forces? So we make the sum of the forces acting on the system 0, and then we can derive equation of motion for mass 1. And similarly, we can also do the same thing for mass 2. Now, you can see the free body diagram shown here on mass 1. Okay, so there's a spring force acting, so K into X, spring constant here is K1. So the displacement of this is X1, the force acting on the system is F1. Okay, so the damper force is C1 into velocity. Velocity, we can write it as X1. So we can write, so C1 into velocity. So velocity is rate of displacement. So we can write X1 dot. So this is the damper force. This is the stiffness force or the spring force. Then the other side we have the block is connected to the another mass M2. So the displacement of mass M2 is X2. So the stiffness, the spring force here will be K2 into the displacement, the net displacement. So the net displacement, we can write it as X2 minus X1. Okay, so the net displacement for the spring K2 will be X2 minus X1. So similarly, the damper here will have the net difference in force, okay, x2 dot minus x1 dot. So this is the difference, net difference in force, okay, V2 minus V1. So V2 is replaced with x2 dot and V1 is replaced with x1 dot. So this is the free body diagram acting on mass 1. So we can now write the forces acting on the system. So we sum up all the forces acting on the system and we equate to 0. So here, okay, So the m1 x1 dot, so this is the force acting on the mass. Okay, x1 double dot is the acceleration. So this is the inertia force. Okay, so which is taken as negative. Okay, then the spring force is also taken as negative, minus k1 x1. Then the force acting on the spring k2, okay, with a net displacement of x2 minus x1, so we can take this as positive. So this is the force associated with the spring k2. Then damper force. So C1 is the C1 into x1 dot is the damping force here, okay, which is negative. So you can see the directional arrow here. So then for the damper C2, so the force is positive. Okay, so the force here is C2 into x2 dot minus x1 dot. So the change in the difference in velocities. So plus the force associated, okay, which we take it as positive in this. So the sum of all the forces will be zero under equilibrium conditions. Okay. Daryl, you want me to record? All right. Okay. Uh, I'm recording the session now. So we are dealing with two-dimensional, 2 degrees of freedom system. So we are trying to derive the equations of motion for the 2 degrees of freedom. Okay, so we can draw the free body diagram for the given system, and based on the free body diagram, so we can apply the Newton's second law. So some of the forces acting on the system to zero, and thus we can write the equations of motion. Now, this equation, now we can write F1t in terms of, okay, we take all the other terms the other side, and we can write the equation of motion for this as m1 x1 dot double dot. Okay, so plus k1 x1, the spring force, plus the damper force c1 x1 dot, minus the spring force associated with the spring 2 k2 into x2 minus x1, minus so the damping force associated with the damper c2. So the whole thing is equivalent to the net force applied on mass. So the net force applied on mass, so based on the free body diagram, so we can write like this. So this is the first equation of motion. Now we follow the same way for mass 2, and we can write the second equation of motion for mass 2. So when you are dealing with mass 2, okay, so you have m2 x2 double dot. So this is the acceleration of mass 2, plus this is the force associated with spring 3 k3 x2. So c3 x2 dot is the force associated with the damper, then k2 into x2 minus x1. So this is the spring force for block 2. So this will be positive for block 2. So similarly, the damping force for block 2, okay, will be positive. So c2 into x2 dot minus x1 dot. So change difference in velocities. So the whole thing is the force acting on mass 2. So therefore, we have the two equations of motion. We can now rearrange these things in slightly a different form, so that we will have a matrix arrangement for these equations. So now this equation 1 and 2 can be rearranged, okay, by expanding the terms, okay. So you can write m1 x1 double dot, then so you can see here c1 x1 dot, then here c2 x1 dot. Okay, so you can arrange these two terms. Okay, so you can arrange c1 x1 dot plus, okay, this also will become c2 when you minus c2 minus x1 dot will be plus c2 x1 dot. So these three terms, so we can arrange like this. So similarly, you have K1x1 here and plus K2x1 here. Okay, so that one you can arrange K1 plus K2 into x1. Okay, then minus C2 into x2 dot as it is you can write, then minus K2 into x2 here you can as it is you can write. So this will be the same equation 1, we slightly rearrange the terms. So similarly we can rearrange the equation 2 and we can write equation 2 as shown here. All right, so now these two equations are the simultaneous equations. Okay, so these two simultaneous equations we can write in a 2 by 2 matrix format. Okay, so we are writing in matrix format as M1, 0, 0, M2. So this is known as the mass matrix. So we are taking M1, M2 here. Okay, so these two we are writing as the mass matrix multiplied by the acceleration matrix. So x1 double dot x2 double dot, this is the acceleration matrix. Okay, so this will be your acceleration matrix. So this is the acceleration matrix. So then we take the C1, C2, then we take minus C2, then C2, or minus C2 and C2 plus C3. So this will be the damping coefficient matrix. So multiplied by the velocity matrix. So this is the x1 dot and x2 dot. So after that, then we have the stiffness coefficient matrix. Okay, so this will be your stiffness coefficient matrix. So then multiplied by the displacement matrix. So this is your displacement matrix. So if you multiply this matrix again, you will get back these two equations. Okay, so only thing is we are writing the two simultaneous equation as a product of matrix multiplication. So when you see here now, this equation can be written in the matrix format in a simple way. So we can write this as a mass matrix multiplied by acceleration matrix plus a damping constant coefficients matrix multiplied by the velocity matrix plus the stiffness matrix multiplied by the displacement matrix. The whole thing is equal into the force matrix. Okay, so what is mass matrix? So mass matrix is 1, 0, 0, and 2. So we are having only 2 degree of freedom system. So that's why you have all these matrices in the form of 2 by 2. So if you're dealing with a 3 by 3 system, then the matrix order will be 3 by 3. So similarly, if you have 4 degree of freedom, so we'll be having a 4 by 4 matrix system. So the order of the elements in the matrix will be very similar to this. Okay, so that is the beauty in arranging the equations of motion in matrix format. So when we want to find the solution for this equation, that means to find out how the displacement varies x1 and how the x2 displacement varies. So the response also we can give in matrix format. Okay, so now what we can learn from this is that a multi-degree freedom systems, sorry, so a multi-degree freedom system, so we can derive the equations of motion using Newton's law, and we can write the equations of motion in matrix format. Okay, so simply when we are dealing with 2 degree of freedom system, so you end up getting a 2 by 2 matrix like this, matrix multiplication. So distinctly we have a mass matrix 2 by 2 multiplied by acceleration matrix plus a damping coefficient matrix 2 by 2 multiplied by the velocity matrix. So plus the stiffness matrix multiplied by the displacement matrix. So the whole multiplication is equal to F1 and F2, the force matrix. Okay, so if you do the multiplication, we can derive these two equations, and of course, we'll get back the equations mentioned above. So these two equations we'll get back from matrix multiplication. So the advantage is that this equation is difficult to memorize. Okay, so in matrix format, very systematic, and without deriving, without applying Newton's law straight away, we can write the equations of motion if we are dealing with a similar um, element systems. Okay, so systems having similar masses, connected similarly as shown in this example. All right. So, guys, any questions on this so far? Anyone? Any questions? Let me know. So don't hesitate. If you don't have any questions, just type no. All right. Okay. Thank you, guys. So then I'll move on. So now we take another example here. So we would like to prove the we take another 2-degree of freedom system. So this is the 2-degree of freedom system here. So here, so there's no damper, only stiffness, masses. Okay, a simple spring and mass system. So here we try to write the equations of motion here for mass m1. Then we know m1 there will be uh, the force acting. Okay, so the acceleration will be downwards as shown here, x1 double dot. So similarly, then the spring force will be upwards. So this will be k1 x1. Okay, but there is a spring k2 also connected to m1. So here the displacement will be okay x1 minus x2. For the spring k2, the displacement will be x1 minus x2. Okay, so we'll be able to write the equation of motion for this mass 1. So the net force acting on that is m1 x1 double dot. So m1 x1 double dot we can and just I think the direction of this spring force will be upwards. Okay. So we take the downward force as positive, then we can write the net force acting on the system is m1 into acceleration. Acceleration we write x1 double dot. Then this net force is equivalent to the spring force k1 into x1. Okay, upward force negative. Then for spring k2, the force is negative k2 into the net displacement is x1 minus x2. So we can write the equation of motion for the first mass m1 like this. Okay, so this will be the equation of motion for mass 1. Okay, so for mass 2, the net force again you can write. Okay, so the spring force is upwards for this. And the displacement here is x2 minus x1. So x2 is the displacement for mass 2. So x1 is the displacement of mass 1. So therefore, for the mass 2, we can write the equation of motion as the net force, that is, m2 into acceleration, that is x2 double dot, is equivalent to 1 minus x1 double dot. So this will be the equation of motion for mass 2. Okay, so we will be able to write the equation of motion as the net force, that is m2 into acceleration, that is x2 double dot, is equivalent to minus K2, that is stiffness constant, into net displacement. Okay, so we can write the two equations of motion for the system, mass and spring system. So like this. So there are no dampers and there's no external force. So these are quite simple to write down. Okay. So then we rearrange these equations. We rearrange these equations like this. So we can write m1 into x1 double dot. So here minus k1 x1, then minus k2 x1. You take the other side. So it will be k1 plus k2 into x1. Then minus k2 x2 is equal to 0. So 0 because there is no external force acting on the system. So the equation 1, once you rearrange, it will be in this form. So similarly, the equation 2 can be rearranged and you can write like this. So this will be your equation 2. So now both the equations, now you can combine and we can write it in matrix format. So here the equation 1 has mass 1, okay, and we write 0, then the equation 2 has mass 2. So the diagonal elements will be m1 and m2. So multiplied by the acceleration. So for mass 1, the acceleration is x1 double dot. Mass 2, the acceleration is x2 double dot. So like this, then for the stiffness constant, so this element we can write it as k1 plus k2, okay, minus k2. So here you have minus k2 and okay, here you have plus k2. So the system can be written as k1 plus k2 minus k2, then minus k2 and plus k2 multiplied by the displacement matrix. So you can write is equivalent to the zero matrix here. So because there's no external force, so the system is having a free vibration. All right. So in simple terms, simple way, we can write uh, the equations as a mass matrix multiplied by acceleration matrix multiplied by a stiffness matrix multiplied by the displacement matrix is equal to 0. So if you encounter any system with like this, so you can straight away use the values here. Okay, so you can straight away use this matrix format and you can straight away write the equation of motion. Okay, so if you have another mass connected, then so this you will have third equation of motion, then you will have 3 by 3 matrix multiplication here. So we can write any degree of freedom. The equations of motion can be written in the form of matrices, a mass matrix multiplied by acceleration matrix plus stiffness constant matrix multiplied by the displacement matrix. Okay, so this is the advantage of the matrix arrangements. So matrix is nothing but arrangement of numbers in rows and columns. So you can see the applications of matrix both in solid mechanics and also in mechanical vibrations. Okay, so now we'll go a bit further into analyzing this mass and spring system, the 2-degree freedom system. So what we have done, the first thing we have applied Newton's method and we have managed to write the equations of motion in matrix format. So now we need to find the solution. So solution means we need to find out what is the x, okay, how the displacement can be equated. Okay, how the response can be found. Again, we'll try to write in matrix format if possible. Okay, so that means the response of this system. So to write the response of the system, first we focus on the two equations. Okay, so we can treat each equation as single degree freedom. Then we can apply the same analysis which we have done earlier. Okay, So we have seen that the response for a mass and spring system, okay, you can consider x1 as a into sine omega t plus phi. So here, this is written in a different notation psi. So this is nothing but phase. Okay. So where omega is the natural frequency. So similarly, x2 can be written as b sine omega 2 plus the phase phi. Okay, we assume both x1 and x2 like this. So now we know the equations for the mass 1. Okay, then what we do? So we take the derivative for this x1 dot and we take x1 double dot. So we differentiate this 2 times. Okay, so then write down in this equation. So replace x1 double dot by differentiating this 2 times. So when you differentiate this first time, you will get a omega sine omega t plus phi. If you differentiate the second time, x1 double dot will be so minus a omega square, okay, sine omega t plus phi. So this represents x1 double dot. So this is x1 double dot. So second derivative of the displacement. Okay, so then K2 plus K1 into X1. So we write K1 plus K2 into, so X1, we are just replacing X1 value here. Okay, so then minus K2 into X2. So K2 into X2 is B sine omega t plus 5. So we are writing this equation. All right, so we are able to write this expression, okay, by replacing x1 double dot value and x1 value and x2 value based on our assumption here. Okay, so this is the equation 1, we can call it as. Okay, then again x2 double dot. So x2 double dot will be so negative b omega square into sine omega t plus 5 plus 5. Okay, the phase. So then plus K2 into X2. So K2 into B sine omega t plus psi. So then minus K2 into X1. So X1 value we write as A sine omega t plus phi. So you will get these two equations. Okay, by substituting the values of X1 double dot and X2 double dot in our equations of motion. Okay, so I clear this, then you can see that in all these terms, okay, so sine omega t phi is a common factor, so you can cancel this. Okay, so once you cancel this, take out the sine omega t plus phi. So the first equation, then rearrange the terms. So the first equation becomes like this. So take out sine omega t plus phi from this equation. So similarly, you can also take out sine omega t plus phi. It's a common factor. So you can put all that under 0, so it becomes 0. So by rearranging and removing the term sine omega t plus psi, so you will end up getting this simple expression. Now, this equation again can be, if you want to solve this, okay, so this is a homogeneous linear algebraic equation. So you need to find out the values of A and B. Okay. So if you put A is equal to 0, B is equal to 0, of course, both the equations will satisfy. And the solution A is equal to 0, B is equal to 0 will give us the equilibrium condition. Okay. So that is not what we want. So to find out the values, okay, for non-zero values for A and B. So now we can arrange this, the determinant of this we need to equate. So this is a mathematical condition. So this we call it as the eigenvalues. So to get the values for A and B, So this determinant should be equated to 0. Otherwise, the simple solution is you get A is equal to 0 and B is equal to 0. So if you solve these two equations simultaneously, but that is not a solution. So to get the solution for A and B, a non-zero solution, so we make the determinant of this as 0. So expand this determinant, okay? So you will end up a fourth order expression like this. So this is a fourth order equation, okay? So, but you can uh, write this as a omega to the power of 4 can be written as omega square whole square. So you can write omega to the power of 4 as omega square whole square. Okay, and omega square can be treated as simply, okay, so you can call omega square as something like lambda. So this one becomes lambda square. Okay, so here omega square you can write it as lambda. Okay, so replace omega to the power of 4 with lambda square, then omega square with lambda. So then this equation is similar to a quadratic equation. So you can equate this equation as a quadratic equation. So you can apply the formula for the quadratic equation. So you can solve the omega square as by applying the minus b plus or minus square root of b square minus 4ac over 2a. So that is the formula for the quadratic equation. So you can apply the quadratic equation, and now we can write omega square as shown here. So the final expression or the final solution for this, we can write omega square in terms of by applying the quadratic equation formula. Okay, so you can write this expression. So now if you solve this by putting the values of k1, k2, m1, m2, then you will get two solutions for omega. So these two frequencies are omega 1, omega 2. So these are called the fundamental or the first harmonic frequencies. So the first harmonic frequencies for a 2 degree of freedom system with a stiffness and matrix. So you can write the expression like this. So this is the solution for uh, mass and spin 2 degree freedom system. Okay, you can see it becomes a bit mathematical. So you need to apply a bit of mathematical analysis in solving the frequencies omega 1 and omega 2. So, but the analysis starts with by assuming the solution in the form of a sine omega t plus 5 for x1 and x2 as b sine omega t plus 5. So since the solution for A and B becomes 0, so to find a non-zero solution, then we write down these equations in this format. Then we get the eigenvalue of this and make it to 0 to get a non-trivial solution. So once you solve this, then you will get expressions for the natural frequencies of the system. So you will get the two natural frequencies, omega 1 and omega 2. So these are called the first harmonics of the system, okay, for the 2 degree freedom system. All right, any questions on this, guys? Let me know. Any questions? Aditya? No problem, no problem. All right, so I clear this, then we move on to the next slide. Okay, so the next slide is deriving the equation of motion for another 2-degree freedom system. Okay, so here you can see the freedom 2-degree freedom system is the two pendulums are connected by a spring. So the spring constant is K. So the two masses considered as only M. Okay. So the mass M has is angular displacement of theta1 and theta2. So the spring, okay, the free body diagram for this you can write, you can draw like this. So this is the free body diagram for one mass. Okay, the weight is acting vertically downwards. So the spring force is perpendicular to this, and the spring force is okay, K into X, right? So spring force is K into displacement, horizontal displacement. So the displacement X can be written as, because these two springs are connected, so the angular displacement of this is theta1 minus theta2. Okay, so you can convert this theta minus theta1 angular displacement, you know the relationship from dynamics, so you can write X is equal to R into theta. Okay, so then we can write V is equal to R into omega. Okay, so similarly, acceleration A can be given as R into angular acceleration alpha. Okay, so these are how the linear variables and angular variables are related. So here kx, so we replace x with r into theta. So theta is the net displacement, which is theta1 minus theta2. So in this case, r is the length a as shown here. Okay, so from the free body diagram, now to get the equations of motion, then we apply the same concept. So because here we are dealing with angular displacements, so the net torque acting on the system must be zero, or the torque due to the forces must be equal and opposite. Okay, so what is the torque? Let us take the first mass M1. Okay, so the torque acting on this will be, how do you write the torque acting on this will be, so I into alpha. So I is the moment of inertia, mass moment of inertia. So for the pendulum mass moment of inertia having a length L, so you can write m into L square. Okay, alpha can be removed, angular acceleration, so you can write it as theta double dot. Okay, so this is the net torque acting on the mass m due to the angular displacement theta1. Okay, so we can write this. Then the counteracting movements will be, okay, due to the weight acting mg. Okay, so mg into the mg horizontal displacement. Okay, so you need to know horizontal displacement, that will be L into theta1. Okay, so we apply the same thing. So in this case, the horizontal displacement for theta1 will be L into theta1. So this is the movement due to the weight or the gravitational force. Then what is the movement due to the spring force? So spring force force is K into X. Okay, then movement means you need to multiply with the perpendicular distance. So for the spring force, the perpendicular distance is again A. So the moment due to the spring force will be K A square theta1 minus theta2. So this is the movement due to the spring force. All right. So for the first mass M, we can apply the net torque, then we can equate with the moments acting on the system due to the two forces. Now the same way we can also write for the other mass, okay, where the angular displacement is theta 2. So we can derive these two equations by applying the Newton's law or by equating the net torque or by summing the total moments acting on the system to 0. Okay, so now we can rearrange these two equations. I clear this in matrix format. Okay, so here m into L square. Okay, so again m into L square. So angular displacements, angular acceleration is theta 1 double dot and theta 2 double dot. So here you have mgl. Okay, so you can take the other side and make it to 0. So this becomes plus mgl, okay, minus k square. Okay, so then you have here minus k square, then plus mgl. Okay, you need to expand this, so you will get k square theta 2 and k square theta 1. So once you expand this, your stiffness matrix becomes like this. Okay, so then theta 1, theta 2 will be your displacement matrix. So you can rearrange this equation 1 and 2 by expanding and again by writing in matrix format. So you can write as shown here. Okay, so we can write the two equations of motion in matrix format as shown like this. The same thing we can abbreviate like a mass matrix multiplied by angular acceleration matrix plus the stiffness matrix multiplied by angular displacement matrix. So this will be the equation of motion for a 2-degree pendulum system connected by a spring having a constant k. So here the two masses are m. So if you want, you can replace with m1, m2. All right. So now to solve the equations means we need to find the response of the system. So that means we need to find out what will be the angular displacement as a function of time, both the masses. So we need to write the solutions for or the response for the two equations of motion as, so we choose theta 1 as a sine omega t plus phi and also theta 2 like this. Okay, so now we take the first derivative and second derivative and replace here. Okay, so we can use these two equations here, this equation 1 and 2. Okay, so we take the first derivative and second derivative. So substitute theta 1 double dot and theta 2 double dot, and theta 1, theta 2 values in equation 1. So you end up getting this equation. So then substitute the values in equation 2, you will get an equation like this. Okay, I'm not going to derive all these things and spend time because that's not productive. So you can always go back and try expand and then try to rearrange. Then you will get these two equations. Okay. Now to solve these equations, other than the non-trivial solution of A0 and B0, then you need to equate the determinant as 0. So once you write down the determinant involves only the constant values here. So it will not have A and B. Okay, so we can replace this A and B and write the determinant with the constants and equate to 0. So then we know how to find the magnitude of this determinant. So again, you will get a fourth order equation like this. But you can always solve this by considering. So you replace omega square with any other value. So let omega square is equal to, let us say, a lambda. then this omega to the power of 4 becomes lambda square. Okay. So this one can be treated as a quadratic equation, and you can apply the quadratic formula to solve. So there will be two roots for the quadratic equation, and the two roots will be as you can see here. So the first harmonic frequency for this system will be so square root of g over L. So g is the acceleration due to gravity. Now the second harmonic frequency is, so it consists of a number of terms. Okay, so this system will have two natural frequencies, omega 1 and omega 2. Then you can find the response, you can find out the amount of those two natural frequencies. All right, so like this, we can apply this type of analysis to solve 2-degree freedom systems or even higher degree freedom systems. Guys, I'll pause for a minute. Any questions? Okay, in the examinations, normally you will not be asked to derive all these things, but you will be using the equations, you'll be applying the concepts to solve some quantitative based examples. All right, any questions or anything not clear, let me know. So the matrix Y is there negative K square here. The main advantage why we are writing like this is because the B coefficient is negative K square. Okay, so you are writing here. So again, the A coefficient is negative K square. So we are writing here. Okay, so the A coefficient here is the whole thing. Okay, so if you you can actually write this as, okay, the idea is to solve these two equations. Okay, and algebraically, if you want to solve, you get both A is equal to 0 and B is equal to 0 as the solution. So to get other than A and B as the solutions, then you have to equate the determinant of these two equations, that is in this format, should be 0. Our aim is to find out the natural frequencies here. So if A is equal to 0, B is equal to 0, that is basically equilibrium condition. So we avoid that. Then to find the solutions for non-equilibrium conditions, so you need to take out the A and B and just take the coefficients determinant. So minus K square in this case, because our equations of motion will have this term negative K square. It is not fixed. It depends on the arrangement of the systems. All right. So in this case, you can, yeah. In this case, the two natural frequencies we can derive. All right. So we'll move further. Okay, let us look at this example now. So this is a 2-degree freedom system. So there are two springs K with constants K. So you are asked to determine the natural frequencies of the system. Okay, then we look into the mode shapes and the nodes for the system. So, so basically there are no values, but the mass is m here, mass is 3m here. Okay, so first thing we need to write the equations of motion for this. Now, this is a 2-degree freedom system. So we can write the equation of motion of this system. Okay. So first we write the mass matrix. So mass matrix will be, in this case, so the first mass is m, so the other mass will be 0. So 0, 3m. So this is the mass matrix. Okay. So then you can write the stiffness matrix. So stiffness matrix, if you see, I'll go back to show you the basic equation. Yeah, yeah. So you can see here K1 plus K2 minus K2, then minus K2 and K2 for this type of system. Yeah. So you can see the stiffness coefficient matrix here. So you can apply this and write the stiffness coefficient matrix. Okay, this one is, so K1 plus K2 means, so you will have 2K, the stiffness matrix. So the first element will be K1 plus K2. So K plus K will be 2K. So the second element will be minus K2. So minus K2 here we write it as minus K. So then you write here minus K2. Then this element will be simply K, K1. So this will be the stiffness coefficient matrix. So now you can write the equations of motion for this. Okay, the mass matrix M0, 0, 3m multiplied by the acceleration matrix. So plus the stiffness coefficient matrix. So 2K is K1 plus K2. Okay, so both are K, so therefore K plus K will be 2K. Then minus K2. So K2 is also K here, so minus K. So here will be minus K2 also. Then plus K, K1 here. So I think plus K2. So K2 is positive, so you can write the stiffness matrix like this, followed by the displacement matrix x1 and x2 is equal to 0. So you can see now the advantage of writing uh, the equations of motion in matrix format. So straight away we can follow the mass matrix as you can see uh, in the previous discussion. So you can follow the mass matrix here, but, and the stiffness matrix here. So we apply the same logic here. So you can see K1 plus K2 in our case would be K plus K. So minus K2 is minus K. So minus K2 is minus K. So plus K2 is plus K. Okay. So it is easy to write equations of motion without going through drawing the free body diagrams. Okay, just by writing the mass matrix multiplied by the acceleration matrix, then the stiffness matrix multiplied by the displacement matrix. So the right hand side will be the 0 because there is no external force acting on the system. So this is about a free vibration. All right. So we can write the equations of motions for this. So then to solve this means we need to find the natural frequencies of the system. So to find the natural frequencies of the system, so later we show that, so you need to do this stiffness matrix multiplied by the displacement matrix minus omega square into mass matrix and displacement matrix. So that everything should be 0. So this equation must be valid. So we need to apply this equation to find the two solutions. Okay, so first we write negative omega square here, negative omega square. So multiplied by the mass matrix here. So the mass matrix. So what is our mass matrix? M0, 0, 3M. So we write the mass matrix here. Okay. Then the displacement matrix. So the displacement matrix for the so this is what we need to find out. The displacement for the first one you consider as 1. So the second one is consider as x. Okay. So then followed by k into x. So this is the stiffness matrix. So then the displacement matrix you consider as 1 and x. So the first displacement is 1, then the second displacement we need to find out. Okay, so now to find out the values of omega, so you multiply this, okay, omega square m plus 2k. Okay, once you multiply this, then you will get the determinant uh, like this. So you need to get the determinant to 0. So this is again the standard formula, negative omega square multiplied by mass m determinant plus the stiffness matrix. So this must be 0. So this is the condition to find the two solutions for the um, 2-degree freedom system. So you multiply this negative omega square m plus 2k, then you will have minus k. So you expand this. So you will get this determinant. Okay, so now to find out the magnitude of this determinant, again you cross multiply with a negative sign, then you cross multiply. Okay, so you will get this expression. So you are equating this to 0. So this you will be able to solve. So you are writing this in terms of a fourth order equation like this. Okay, so if you rearrange the terms, so you will get 3m into omega to the power of 4. Then negative 7mk into omega square. So this will be plus k square, whole thing will be 0. So this is a fourth order equation. Now to solve this fourth order equation, so you substitute lambda is equal to omega square. Okay, and also you substitute phi is equal to k by m. Okay, so because you have here k square, so you can consider phi as k by m. So this equation reduces to a quadratic equation like this. So this is how, by substituting lambda as omega square and phi as k by m, so this fourth order equation can be converted into second order equation. Okay, so once you have the second order equation, then you can apply the quadratic formula, then you can solve this. So you will get two values for lambda. So you can solve this using quadratic formula. Okay, so you will get two values for lambda. Okay, so once we take the positive sign here, the other one with the negative sign. Okay, so but now we substitute omega as square root of lambda and replace phi with k by m. So once you substitute back, then your omega 1 becomes like this. So that means your first frequency is 0.391 square root of k by m. Then your second frequency is 1.47 square root of k by m. Okay, so this is how we can solve a 2-degree of freedom system. Okay, I'll show you. This is the problem. Okay, to solve this problem means to find out the two natural frequencies for the system. So we write the equation of motion. Okay, so once you write the equation of motion, to find the solution, you need to find the determinant of negative omega square m plus k is equal to 0. So this is a condition later we can prove. Okay, So to make this condition z, okay, so we multiply mass matrix with omega square. Okay, so we write the K matrix. So then the determinant of this omega square m plus K we equate to 0. So then you end up getting a fourth order equation, then with appropriate substitution. So in this case, we use the phi as K by m and lambda as omega square. So this fourth order equation reduces to a quadratic equation. So this quadratic equation you can solve and you will get the two roots, okay, omega 1 and omega 2. All right, so this is how we can solve a simple 2-degree freedom systems. Guys, is that clear? Any questions? We'll be discussing about some more examples later. So now we are discussing the multi-degree freedom systems. So now we know how we can draw the free body diagram and derive equations of motion. But we can see there is a trend for multi-degree of freedom systems to write equations of motion. So for the systems, we can always write a mass matrix M multiplied by the acceleration matrix, okay, plus, okay, the stiffness matrix, so multiplied by the displacement matrix will be 0. So this is a standard format when you're dealing with a mass and spring system for multi-degree freedom. So we can write the equations of motion like this. Okay, so if there is a damper, then you can also have the equation indicating the damper. So you can write m into, so I write x double dot here, the acceleration matrix plus the damping coefficient matrix C multiplied by the velocity x dot. So then you can write plus stiffness matrix K, then multiplied by the displacement matrix X, okay, is equal to 0. So this is for a damped and free vibration. So this is for a damped free vibration. So this 0 can also be written as matrix. So because if you have 2 degree of freedom, then you have 2 by 2 matrices. Every term is in matrix format. So this will be a 0 matrix. So if you are dealing with a forced vibration, then this matrix will be a forced matrix. All right. So the next important aspect in multi-degree freedom system is we can also derive equations of motion without using the free body diagram. So we use the energy method. We have applied for single degree freedom system. We can also use the same energy method for multi-degree freedom systems. Okay, and this method is popularly known as the Lagrange's equation method. Okay, so Lagrange's equation method is nothing but the energy method to derive equations of motion for multi-degree freedoms systems. Okay, so the Lagrange's equation you can write in two forms. Okay, the first form you can write like this. Okay, so here you can see this symbol dou. Okay, so this indicates a partial derivative. Okay, so d by dt is a full derivative. Okay, you can see this is d by dt of this plus partial derivative of kinetic energy, okay, with a variable qi. then partial derivative of potential energy, then plus partial derivative of the dissipation energy. Okay, so dissipation energy includes the dissipation constant C. Okay, overall is equivalent to the force acting on the system. Okay, so if you have two forces, then you can say Q1, Q2. So three, then Q1, Q2, Q3. So accordingly, the change here. Okay, so you can also write for a conservative system. So where there is no dissipation energy here, then you can write the Lagrange's equation as a Lagrangian. So you can take L as the difference of kinetic energy and potential energy. So Lagrangian L is Ke minus Pe. So kinetic energy minus potential energy. So then we'll take the partial derivative of dou L by dou Qi. Okay, so this is the whole expression. So first find out what is L, then take the partial derivatives and as shown by this expression. So we'll be applying this equation when we have the dissipation energy. Otherwise, if you don't have the dissipation energy, simply uh, okay, the condition should be, it should be a conservative system. Then you can apply the Lagrangian L, Ke minus Pe. So basically, this Lagrange's method is energy method, but it involves application of partial differentiation. Okay, so I'll try to explain these equations with the following examples. So let us focus on the examples first. So before we go into the example, what is a function? Okay, so why we are talking about partial differentiation. Now, when we write a function x, y, z, okay, this is what we have written. So that means the value of this function depends not only on x, but also on y and also z. So it is a function with three variables. So here the variables are x, y, and z. So the value of this function depends on these three variables. So we cannot have a full derivative for these type of functions. Okay, so all the time we have functions only when we have y is equal to fx. So y value depends only on the variable x. So you have only one variable. So if you have y is equal to 3x squared, okay, so then you can define dy by dx. So this is a total derivative because the y value only depends on x value. So in this case, you can write, okay, as 6x, the first derivative. So this is a total derivative. So we can define total derivatives when the function has only one variable. But there could be cases where the function has more than one variable. You can see an example here. Okay, so in this case, the function is given as x cubed y to the power of 4 z to the power of 5 plus x plus y square plus z cube. Okay, so now for these type of functions, we can only take the derivatives partially. So that means we can take the derivative of the function f with x by keeping the other two variables constant. So here when I write a dou f or dou x, so that means I am keeping the y and z variables as constants. So when you take the derivative, I only differentiate the function with respect to x and treat all the other variables as constants. Okay, so now you can see when I take the derivative of this function with respect to x, so I only take the derivative for x. So x cubed becomes 3x squared. So the other variables, y to the power of 4, z to the power of 5, we treat as just constants. So we just write y to the power of 4, z to the power of 5. Okay, then again this term, so derivative of x with x, so you get 1. Okay, then derivative of y square with x, so y square is a constant, so the derivative of y square with respect to x will be 0. So similarly, the derivative of z cube with respect to x will be 0. So that means the partial derivative of this function with respect to x will be 3x square y to the power of 4 z5 z to the power of 5 plus 1. Okay, so you can take the second derivative of this function if you want. So you can write the second derivative of this function as dou square f over dou x square. So if you take the second derivative of this function, what happens? Can someone tell me the value for this second derivative? So I can only differentiate with respect to x. So 3x square, if I do, that will be 6x. Yeah, that's correct. So y to the power of 4, z to the power of 5. Then the 1 will vanish because the differentiation of 1 with x is 0. Okay, so similarly, okay, now we can differentiate the function with respect to y, let us say. So you want to differentiate with respect to y. So when you are differentiating with respect to y, only the y term will be differentiated, other terms will remain constants. So when you differentiate y to the power of 4, you get 4y cubed. Then the remaining term x cubed and z to the power of 5, they just will be constants here. Okay, then you can't differentiate the x with respect to y, so it will be 0. Then y square I can differentiate with y, so this will be 2y. Then z cubed I cannot differentiate, so value will be 0. So this is how you can write the partial derivative of the function f with respect to y. Okay, so if you want, you can take the second derivative of this. So you can take the second derivative of this function. I write dou square f over. So now I want to take the derivative of this with respect to x. So I write dou x and dou y. So already I took with differentiation with respect to y. So now can someone give me the answer for this second order partial differentiation? So now take note that I'm differentiating with respect to x. Anyone? Okay. Someone giving me? Yep. Yeah. So this 4x cubed becomes 12x squared. Then you can keep the y cubed z to the power of 5 the same way. Uh, there is no 2y because you cannot differentiate y with respect to x. So plus 0. Is that clear, DJ? See, DJ? Yeah. So it will be only 12x square y cube z to the power of 5. Okay. So I clear some of this, and now can you look for the partial derivative of this term, this function with respect to z, the last one. So if you differentiate the function with respect to z, only the z term will be differentiated. So z to the power of 5 becomes 5 into z to the power of 4. So you will have 5x cubed y to the power of 4 and z to the power of 4. So the second differentiation of x with z will be 0. So differentiation of y square with z will be 0. Then differentiation of z cubed with z will be 3z square. Okay, so this is how you can do the partial differentiation. So partial differentiation comes into picture because when a function depends more than one variable, then we cannot define full derivatives. We can only define partial derivatives. So at a time, we can take differentiation with respect to one variable, keeping the other variables as constants. So therefore, we call this process as partial differentiation. Guys, any questions? I'll pause here for a minute. Any questions? All right. Okay. Then we move on to how we can apply the Lagrange's equation. So we'll try to understand this by this example. So now consider the system, the multi-degree freedom system here. So guys, can you tell me what will be the degree of freedom here? Anyone, the degree of freedom here? What is the degree of freedom? Yes. So this is a 3-degree freedom system. Okay. So we draw the free body diagram here. So for the mass M1, so this is the spring force. Okay. So here the spring force is 2k into x2 minus x1. So x2 minus x1 is the net displacement for spring 2k. So similarly for 2m, so 2k into x2 minus x1, but it acts in opposite direction. So here, the displacement is, net displacement is x3 minus x2. So similarly for mass m, so it will be k into x3 minus x2. So there's an external force acting here, F2, F function of time. This is the external force Ft. Okay, so the displacements of these things are x1, x2, x3 shown. Okay, so here the spring force will be 3k into the displacement x3. Okay, so this is the free body diagram. Uh, this only helps us to find out the energies, okay, easily. So now we'll write what is the total kinetic energy in the system. Total kinetic energy in the system. So for the mass m, okay, half m v1 square. So v1 is the velocity of mass m. So you can write half m x1 dot square. So for mass 2m, so half m 2m x2 dot square. Okay, so 2m is the mass, so x2 dot square is the velocity. All right. So you are calculating the total mass, total kinetic energy. So for the third one, so half m x3 dot square. So this is the total kinetic energy. So essentially, we are writing the total kinetic energy of the system, and we are calling it as capital T. So then what is the total potential energy of the system? So total potential energy, so you can call it as V. Okay, so potential energy will be due to the spring forces. Okay, so for the first spring, okay, so for the first spring, the potential energy will be half K x1 square. X1 square will be, the x1 is the displacement. So the spring force is K into x1. The energy will be half K x1 square. So you should be knowing this from your dynamics course. Okay, so this is the energy due to the spring K. Now the energy due to the spring 2K potential energy. So half 2K into the displacement net x2 minus x1 whole square. So similarly for the third spring K, so the kinetic energy will be half K. So the net displacement is x3 minus x2. So the displacement square. Plus for the last spring 3K, so half 3K into the displacement for this is x3. So x3 square. So the total potential energy for the system you can write by the equation B. So is that clear, guys? So equation A represents the total kinetic energy in the system, and equation B is the total potential energy in the system. So we now write the Lagrangian L. So L is nothing but T, the total kinetic energy minus the total potential energy. Okay, so as you can see the previous example, so L is kinetic energy minus potential energy. Okay, so we apply here L. So you just write down everything. Okay, that is the equation for Lagrangian L. Guys, is that clear? So we are writing the total kinetic energy in the system, and we are writing the total potential energy in the system, and now we are writing the Lagrangian as the kinetic energy minus potential energy. So we write L is equal to T minus V. So that gives us this equation C. So the equation C is nothing but Lagrangian. All right. So now to apply the uh, Lagrange's equation, so this is the expression. So d by dx of the partial derivative of Lagrangian with respect to x1 dot velocity minus the partial derivative of the Lagrangian with respect to the displacement x1. Okay, so this is the basic or the guiding equation. Okay, so now we take L. So L is this expression. Okay, so L is this expression. So I'll try to explain the first what we are doing. Partial derivative of this L with respect to x1 dot. Sorry. So partial derivative of L with respect to x1 dot. So now from this, if you want to take the partial derivative of this expression with x1 dot, with the velocity. Okay, so only the x1 dot terms you need to differentiate. So here, if you differentiate this x1 dot square, okay, so this one will be 2m okay, so you will get x1 double dot. So as you can see here, okay, now 2m x1 dot only. Okay, so the first term 2m x1 dot. So you have 1 over 2 is multiplication factor, the whole thing. Okay, 1 over 2 is coming. Now, can you take the derivative of this, partial derivative of this? Guys, there is no x1 dot term here. So the partial derivative of this term will be 0. Similarly, the partial derivative of this term will be 0. So you can see that there is no x1 dot anywhere else. Okay, so therefore the partial derivative of this will be, you cancel this 2 and 2, it will be m into x1 dot. Okay, so only the first term you can take the partial derivative with respect to x1 dot. So that is what you can see here. Okay, so this term will give you the partial derivative of L with respect to x1 dot will only get m into x1 dot. Okay, so minus the partial derivative of L with x1. So I'll go back again here, this expression. Okay, so now I clear this. Okay, so now we need to take the derivative of this term with respect to x1, right? So dou L over dou x1. So we take the partial derivative of L with respect to the variable x1. Okay, so I just keep half as the multiplication factor. So you can see the first term involves x1 dot, x1 dot. So the differentiation of this with respect to x1 will be 0. So similarly, the differentiation of the second term will be 0. The third term will be 0. But here k x1 square. So this term will give you 2k x1. Okay, so here you will have negative 2k x2, then minus my, okay, this one is the whole square. So you can expand this. So if you expand this, you get negative 2k. Okay, so you can write x2 square minus plus x1 square minus 2 x2 x1. Okay, so this is x2 square. So now you can differentiate this because it has x1 terms. Okay, so when you differentiate this x1 term, so you will get 2x1. So 2x1 into minus 2k. So you will get minus 4k x1. Okay, so this 2x2 x1, if you differentiate, you get 2x2. So 2x2 minus 2k, it becomes minus 4k x2. So that means you can write this as a half. Okay, so 2k x1. Okay, you can take minus 4k. Okay, you can write it as x2 minus x1. Okay, so this is the partial differentiation of the Lagrangian with respect to x1. So now you can see the same thing is written here. So this negative partial derivative of L with respect to x1 is shown the whole thing. Okay, so now if you simplify these two terms, so when you take the derivative of this with x1 dot, so you will get x1 double dot. M will be constant. So differentiation of this with respect to x will be the second derivative, okay, d by d. So you are taking the derivative with respect to time. So you will get second derivative. So plus, so rearrange everything, then this will be your first equation of motion. So here you are taking the partial derivatives with x1 and x1 dot. There's a minor typo error here. So this one should be dt. So please take note that this here is dt. Okay, so if you take the partial derivatives with x1 and x1 dot, you will get your first equation of motion. Then if you take the partial derivatives with respect to x2 and x2 dot, then you will get the second equation of motion. So this will be your second equation of motion. Then similarly, if you take the derivative with respect to x3 and x3 dot, okay, the velocity x3. So then you will get the third equation of motion. So this is how you can apply the Lagrange's method, okay, to get equations of motion for multi-degree freedom systems without applying the Newton's law. So normally in the exams, there will be definitely one person dealing with Lagrange's method. So you will be having a system, then you need to apply Lagrange's method to derive equations of motion. Uh, Guys, let me know if you anything is not clear, then I can go through once again. Otherwise, it is basically a mathematical partial differentiation of energies. So for any given system, you need to write the total energy, potential, and kinetic, take the differentiation. Then, depending on the number of systems, you take the partial derivatives. So first partial derivative, it will be with x1 and x1 dot. The second one with, okay, so you can apply this expression. Okay, so we have seen the example for this. So similarly, this example is also no different. So if you are dealing with dissipation energy also, so you can take here the partial derivative of Ke with dou Qi dot. Okay, dou Qi dot. So let us say you are dealing with 2 degrees. So Qi dot will be your x1 dot. So Qi will be your x1. Okay? So all these things are partial derivatives. Only the first one, okay, you are combining the partial derivative with a total derivative. So you're combining the partial derivative with a total derivative. So this is the standard Lagrange's equation. Okay, so we apply these equations to derive equation of motion. Because most of the time deriving equations of motion using energy method is simpler. So therefore this Lagrange's method are very popular for deriving equations of motion for multi-degree freedom systems. So you need to have some familiarity with the basic differentiation and basic partial differentiation. Okay, so this is a prerequisite knowledge. I think most of you will be knowing it. And those students who did the bridging program, we discussed all these things in the bridging course. All right, so I move on. Any questions before we move on to the next problem? Yes. So we'll be going through because there is a assignment question on this. Yes, no, Raza, we'll be going through. All right. So before we go for a break, so we can go through this example. We have derived for this example the equations of motion using the basic Newton's law, applying the torque and moments. Okay, so now we can take the same example and apply the Lagrange's method. So for applying Lagrange's method, so we take the Lagrange's equation, okay, the partial. So d by dt of the partial derivative of kinetic energy with dou qi dot minus the partial derivative of kinetic energy with the dou qi dot plus the partial derivative of potential energy with dou qi dot. So the sum is 0. So now to apply this, first we write what is the kinetic energy in the system. Okay, so the kinetic energy in the system. So the kinetic energy due to the mass is m into v square, right? Half m v square. So v will be, as I said, we can write v is equal to r into theta. Okay, so v1 will be r into theta 1. So v1 square will be r square into theta 1 square. So therefore half m1 v1 square. So v1 is replaced with L square theta 1 square. So for the other mass, m2 into v square. So I clear. So this will be the kinetic energy due to the velocity of masses. Okay, so spring will not have any kinetic energy. Okay, then the potential energy is both due to the gravitational force here and also due to the spring force. Okay, so for the first mass, here we can call it as m1 and m2. Okay, so we can write the gravitational force is weight m1g. Okay, into h. So you need to write mgh, right? So here h is when you have angular displacement theta 1 or theta 2. So h can be written as the total length of the string here is L. Okay, so you can write this as L into 1 minus cos theta 1. Okay, so this is a simple geometric relationship. So we need to know what is the height of the pendulum from the horizontal. So from the horizontal, what is the L? So the total is L. So the difference will be L cos theta. So that's why this H becomes L into 1 minus cos theta. So the potential energy due to the mass M due to the weight m1g will be m1g into L into 1 minus cos theta 1. So similarly for the other mass, it will be m2g L into 1 minus cos theta 2. For the spring, it is half k x square. So here, for the spring, the displacement is theta 1 a into theta 1 minus theta 2. So the energy, you can write it as half k x square. Okay, so x is a theta 2 minus a theta 1. Okay, so this square you need to add here. So this is the potential energy in the system due to the weight of the masses and also due to the spring constant. So now we can apply the Lagrange's equation. So the first part of the Lagrange's equation is d by dt of the partial derivative of Ke with theta 2. Okay, so theta 2 dot. So we need to take the kinetic energy. Okay, so the kinetic energy, this one, you are taking the partial derivative with theta 2 dot. So the first term will not have any value. So the first term will give you 0 because you are taking the partial derivative with theta 2 dot. So if you take here theta 2 dot square, so it becomes 2 into theta 2 dot. So the 2 will get cancelled. So the partial derivative of this will give you only this portion, okay, m2 L square theta 2 dot, okay. So now this partial derivative, you are taking the differentiation with respect to time. So m2 L square will be constant, okay. Then this theta 2 dot, if you differentiate with respect to time, so it becomes theta 2 double dot. So it becomes theta 2 double dot. All right. So you can see that the partial derivative of the kinetic energy with respect to theta 2 dot will give you m2 L square theta 2 dot. Then the partial derivative of kinetic energy with theta 2 will be 0 because none of the term has theta 2. Okay, so none of the term has theta 2. So similarly, if you take the partial energy, a partial derivative of potential energy with respect to theta 2, okay, so the first term will be 0, then the second term will have m2gl sine theta 2. So this cos theta 2 becomes sine theta 2. Then, yeah, half k into a theta 2 minus a theta 1. So this becomes 2 times. So the 2 will get cancelled. So you will have a square k into theta 2 minus theta 1. So add up these three things. Okay. The second equation of motion will be this equation. Okay. So similarly, you can also prove that by differentiating with theta 1 dot. Okay, so you can, the first equation, you can show that this is, so this will be your first equation, and you will get your second equation here. So combining these two equations, so you can write in the matrix format. So a mass matrix multiplied by the angular acceleration matrix. So here, mass matrix, you can see, will have the value ml square. Okay, so your mass matrix will have ml square 0 and 0 ml square. Then the stiffness matrix will have mgl. Okay, so here m1 and m2 is equal to m. So we are not using 1 and 2. So you can write the stiffness matrix like this, multiplied by the angular displacement matrix. So this one you can compare with your Newton's method. So both the equations are identical. Okay. Uh, Sometimes it is advantageous to use Lagrange's method, because if the system is complex, then applying the Newton's law becomes a bit more complex. Guys, any questions on this? So this is the application of Lagrange's method or the energy method to derive equations of motion for multi-degree freedom systems. So there's another example. You can go through this example, very similar. Okay, so all the potential energy, kinetic energy, dissipation energy, all are shown. Then the partial derivatives. So step by step, the applications are shown. So then you can see the derivation of the first equation of motion, then the second equation of motion, and the third equation of motion. So you can combine all the three equations and you can write in the format of the matrix form. So this is the very first examples which we have done using the Newton's method. All right. So now the time is nearing 8:30. We'll go for a break. Okay. Then we'll meet at again 8:45. All right. So I see you guys at 8:45. Hi guys, hope you're back. All right. Okay. What others? All right. Guys, the next part of the thing is to find the solution for 2-degree freedom systems. So now a 2-degree freedom system can be written like this. So we are dealing with free vibration. So free and undamped vibration. So multi-degree freedom system, free and undamped. Free means there is no external force. Undamped means there is no damper. So we are dealing with only mass and spring system. So for a mass and spring system, we can write the equation of motion in matrix format. So we can write like this. And the same thing once you expand, we can also write like this. Now, the solution for or the response for the 2-degree multi-freedom system, we take the response in the format of matrix and we take the response as x1, x2 exponential power e I omega t. Okay, so if you substitute this here, exponential power I omega t is cos omega t plus I sine omega t. So you can replace that with sine omega t plus phi. So once you substitute back this into the equations by taking the second derivative and the displacement, okay, you can get this expression. Okay, so normally we write this as negative omega square, the mass matrix, okay, and displacement, the response. um, this is also matrix minus, okay, plus kx is equal to 0. So we just replace the terms. So x is again the displacement. Okay, so the solution can be written in this format. So here, if you elaborate this, now we write negative omega square here. The mass matrix is replaced, then the displacement matrix is written, plus the spring matrix and the X matrix, okay, the displacement matrix. So to solve this, okay, uniquely without non-zero solutions, so you can write this uh, by just multiplying everything and adding the matrices. So you'll end up with this matrix. Now, to get a non-zero solution for x1 and x2, so the determinant non-trivial solutions, the determinant must be 0. So to get the response, so you must find this determinant, you must equate this determinant to 0. So to solve the displacements, always we assume that the first displacement is 1. Then you can find the second displacement in terms of the first displacement. Okay, and in the earlier session, we have seen how to get the two frequencies, omega 1 and omega 2. Okay, so now depending on the frequencies, for frequency 1, you can get the displacement to 1 by using this expression, and the displacement 2 you can get by this expression for the omega 2, the second natural frequency. Okay, so therefore you can write the total response in terms of the matrix format. So you can write like this. So the first one is for uh, frequency omega 1. So the second one is for frequency omega 2. Okay, so this is the mode shape one for omega 1, and this is mode shape one for omega 2. So change this to 2. All right, so these expressions, the derivation is not important, so you can always use the expressions to calculate the amount of displacement. So for two frequencies, so you have the two displacements. Okay, the mode shape refers to, how the displacement varies with respect to 1 1, and how the displacement 2 2 varies with respect to 1 2. So the variation of displacement is referred as the mode shape or the modal shape. All right, so uh, this particular analysis tells you, okay, the two important things in this is uh, the first one, to write this expression equate to 0, okay, to solve the displacement matrix X. Okay, then once you solve, okay, for the two frequencies, omega 1 and omega 2, the mode shapes you can calculate based on this formula. Okay, always the first displacement we take it as 1, then the second displacement we calculate in terms of the amplitude 1 here. So the same way for the second frequency also. So this one is for omega 2. All right, so this expression is important for you. Okay, so let us look at this example here. So you can see this is a 2-degree freedom system. There are two masses. The first one is m. So the second one is 3m. So the displacement is x1 and x2. So the spin constants are k and k. So for this, we can write the equation of motion in matrix form. Okay, the matrix the mass matrix M0, 0M. So this is the mass matrix, followed by the accelerations x1 double dot and x2 double dot matrix, plus the stiffness matrix. So the stiffness matrix is always K1 plus K2 minus K2, then minus K2 and K2. Okay, so here you can see the first one, K plus K will be 2K here. Okay, then minus K2 is minus K, okay, minus K, then plus K2 is plus K. So this one will give you the stiffness matrix multiplied by the displacement matrix. Now to get a unique solution for this, okay, so to get a unique solution for this, we apply the equation negative omega square mx minus km, kx will be 0. Okay, plus kx is 0. So the mx are the matrix. Okay, so the mass matrix, displacement matrix. Okay, then the stiffness matrix and displacement matrix. So we apply this equation. Okay, so then you multiply here. So omega square m plus 2k, then you get okay, minus m omega square plus 2k minus k. So you will get the first one. So you can simplify this and you can write this expression. Okay, so now to find the values of x1 and x2, so this determinant is equated to 0. And you can find the value of this determinant, and you can cross multiply and you can write this expression. So now solving this equation, you will get the two frequencies omega 1 and omega 2. Okay? So once you know omega 1 and omega 2, so you can apply the formulas for the mode shapes. Okay, the previous slide I have shown you the two formulas, so you can use the two formulas. So you know all the values here, omega 1 square, 1 k1, all the values are there. Omega 2 is, so you know omega 1 and omega 2. So substitute back these things, so you will be able to get the mode shapes for the two frequencies. Okay, it is just okay, following uh, writing down the equation of motion, then applying the negative omega square mx plus kx is 0, then making the determinant 0, then from the determinant you will get the quadratic equation, solve the two equation, you will get the two frequencies. So once you get the two frequencies, then you can get the mode shapes from the equations which we discussed earlier. All right, so put back all the numbers. Normally in the exams, you may be knowing the mass values. So you'll know the omega 1, omega 2 values. So substitute into the equations and you will get back the answers, the mode shapes. All right. Okay. The next part is to find the vibration response. So free vibration response. Okay. So what we got is only omega 1 and omega 2 we got. Then we got the modal shapes. So x11, x12, x21, x22. So the displacement values we got. So now to get the response of the system, how we can write the response, okay? How you can write the response of the system, the displacement in terms of the given um, parameters. So to get the response, so what we do is we choose the response of the system like this, x into sine omega t phi. So for a 2 degrees of freedom, so the natural frequencies we can take omega 1, omega 2. So now the response for this you can write in this fashion. So let us assume that the response can be written as a1x1 into sine omega 1 t plus phi 1 plus a2x2 into sine omega t plus phi 2. So what are the unknowns here? A1, A2, then phi 1, phi 2. So you need to get A1, A2 values and the two phases phi 1 and phi 2. So to find these values, okay, so you need to get the initial conditions. So if you know the initial conditions, for example, the initial conditions are given here. Okay, so x1 when time t is 0, so let us say the value is x10. So x2 when time 2 is 0, the value is, let us say, x2 0. So similarly, when the time is 0, the x1 dot, the velocity is, so let us say the value is known. So all these are the initial conditions, means when the time t is 0, the displacement and the velocities of the values are known. So if you know these things, then you can apply these things. So you can calculate A1, A2 from these formulas and phi 1, phi 2 from this formula. So where C1, C2, C3, C4 all given here. So based on the initial values and based on the model shape values. So let us say you know all the values here, x10, the initial condition, x22 is the model shape, okay, x20 is the initial condition. So all these things will be known. Then you can calculate C1, C2, C3, C4. So substituting these equations, you know a1, a2, phi 1, phi 2, then substitute these values here, then you will get the response of the system. Means how the system responds uh, with respect to time. So you can express mathematically. So similar things we have done for single degree of freedom systems. Okay, now this analysis is for 2 degrees or even for higher degrees. But as the higher degrees goes, then there will be more constants and there will be more complexity into the problem. So this is applicable, this analysis is applicable for a 2-degree freedom system. All right, so there's an example given here. So this example we can just go through. So the initial conditions are given here. So we take the previous example. So here, when the time 0, then the displacement x1 is given as the value delta. So the velocity of the first mass, the displacement is v1 is given 0 when time is 0. So similarly, the displacement 2 is given as 0. When the time 0, the displacement is negative of delta. Okay, the velocity is 0. So these 4 are the initial conditions. So once you know the initial conditions, so the modal shapes for the previous problem, we are taking only the previous problem. Okay, so the modal shapes are given in the previous problem. So now you substitute, use these equations, C1, C2, C3, C4, substitute all the values and calculate. So you calculated C1 and C2 is 0, C4 is 0, C3 is calculated. So from there you can calculate phi 1, phi 2, A1, A2. So once you get all these values, then you can write the free response solution in matrix format like this. So just substitute all the values and that will be your final response for a 2-degree freedom system with a mass and spring system with no external force. All right, so substituting the values into the equations. Okay, so this topic, the free vibrations of multi-degree freedom system, the natural frequencies, mode shapes, and free vibration response. This we'll do maybe tomorrow or if time permits later. But now we can go back to the assignment questions. So in the last session, we have attempted the first two questions. No, I think we stopped in the midst of this problem. All right, guys, could you work on this problem or shall I go through? Shall I skip this or you want me to do? Okay, so we'll go through then. So this problem is all right. Okay, guys. So there's a last industrial exhaust fan is mounted on a lightly damped steel frame. So uh, steel frame means basically the damping ratio is small. So eta is small. So the plant manager has decided to mount a storage bin on the same platform. So you want to increase the weight of the platform. So once you increase the weight, the natural frequency of the system changes, right? So adding mass to a system can change its dynamics substantially, and the plant manager wants to know if this is a safe change to make. So to find out that, he needs to have the system properties. So if he doesn't have the system properties, then he needs to measure the response of the system and find out. So he did the response of the system. Okay, so he measured the floor amplitude of the floor at several different motor speeds so that he wants to measure the system dynamics. So no resonance is observed in running the fan from 0 to 500 RPM. So there is no resonance between these 0 to 500 RPM. So then deflection measurements are made and it is found that the amplitude is 10 mm at 500 RPM and 4.5 mm at 400 RPM. So he know the amplitude at different rotations per minute. Okay, one is 10 mm, the other one is 4.5 mm. So the mass of the fan is given 50 kg, and the plant manager would like to store up to 50 kg on the same platform. So he wants to increase the mass from the present 50 to 100. So the best operating speed for the exhaust fan is between 500 to 500 RPM. So this is the best operating speed. Now, based on the data which the plant manager has measured the amplitudes at two different frequencies, whether he is justified to add the mass or not. Okay, so if he cannot add the 50 kg, then how much he can add? So this is a a problem based on the response of the system. Guys, I'll use the camera because if I start writing, then it will take a long time. All right. Okay, so to begin with, for steel frame, okay, so for steel frame, So we can say the damping ratio is small. So normally when the damping ratio is small, okay, the amplitude ratio, so the amplitude ratio x by y can be given as, okay, so 1 over 1 minus r square. So the amplitude ratio expression can be um, simplified when for small damping ratios. So you can write it as 1 over 1 minus r square. So, and also it says that from the description, okay, no resonance is observed. So no resonance is observed between 0 to 500 RPM. So this is given. So that means no resonance means ratio of, so no resonance implies the R is less than 1. So the ratio of frequencies will be less than 1. Okay, so when, okay, given omega is 500 RPM, when omega is 500 RPM, so convert this into radians per second. Okay, x is equal to, the amplitude measured is 10 mm. Okay, so now from this expression, okay, so x we know, okay, we can write 10 is equal to, so y over 1 minus r square. Okay, so guys, let me know how much is 500 RPM in terms of radians per second. So we know that R is ratio of frequencies omega over omega n. So let me know what is omega. Can someone tell me? So Safaruddin says 52.35 radians per second. Okay, so you can use 52.35. So R becomes 52.35 over omega n. So that means you can write this as y over 1 minus 52.35 over omega n square. Okay, so this 10 is, you can write, so you can call this as 10 is equal to y over 1 minus, so you can call this as your equation 1. Because there are two unknowns, we can't solve this equation. So we need to have one more equation. Now the one more equation is that when the amplitude is 4.5 mm, okay, so omega n is given as, omega is given as 400 RPM. So 400 RPM convert into radians per second. All right, so 41.89 radians per second. So we can write the second equation, okay? So 4.5 is equal to y over 1 minus 41.89 over omega n square. So you call this equation 2. Okay, so solve equations 1 and 2. To get both the natural frequency and the y amplitude. So you can find out from those two equations these two. So guys, you would like to solve this and let me know your answer. I think guys, it may take some time for you to calculate, okay? Therefore, I'll leave it to you. Then I'll proceed with further analysis. Is that okay? All right. So you calculate the natural frequency and the y amplitude. After that, okay, so you can calculate the spring constant. So once omega n is calculated, so spring constant of the platform, so K can be calculated as m into omega n square. Okay, so K known. So now you know K. Okay, so increasing the mass to 100 kg. So you can calculate the natural frequency of the system. So you can calculate as K over 100. Okay, so you will get some natural frequency of the system by adding another 50 kg on the platform. Okay, so now this natural frequency, you need to find out how much you will get this natural frequency. If this natural frequency falls in the normal operating range, then resonance will take place. So you need to make sure whether this natural frequency falls within the normal operational range or not. So if it falls within the normal operational range, then definitely resonance will take place. So therefore, you need to avoid this. So that means you cannot increase the mass to 50 kg. So if omega n falls in the normal operating range, so resonance will take place. So resonance will happen and should be avoided. So you need to check whether this natural frequency, by increasing the mass, will fall in the operating frequency. So that is between 400 to 500 RPM. So if it falls, then we need to avoid. That means you cannot add the mass. If it doesn't, then we can add the mass. So you can give your conclusion. All right. So after that, you need to find out what should be the range of the mass that can be added. So the range of the mass that can be added, so you can write so range of the mass that can be added. So you need to make sure that the natural frequency is your K, whatever the value you calculate, over 50 plus whatever the mass you can add. Okay, so this should be the square root of this, square root of this. Okay, so this should be less than the 400 RPM. So 400 into 2 pi over 60. So convert into radians per second. Otherwise, on the higher side, it should be omega n should be K over 50 plus this mass should be greater than 500 RPM. So 2 pi over 60. So you can find out the mass should be less than something. Okay, mass added should be greater than something. So you can calculate these values. Okay. So guys, you can do the calculations because some of the calculations will take time. Let me know if you have any questions. Otherwise, we'll move to the next one. Is that clear? Any questions, or can I go forward? Nurada says, okay, so you have noted down everything, right? All that. Okay. How about any? All right. Okay, Vinod. So then we'll move on to the next question. Okay, this is a okay multi uh, degree of freedom, 2 degree of freedom. So two subway cards are shown here with a mass of 2000 kg and are connected by a coupler that can be modeled as stiffness constant. Okay, K is 28,000 Newton per meter. Now you're asked to use Newton's law to derive the equations of motion, then calculate the natural frequencies and determine the associated mode shapes. So you need to draw the free body diagram first, because whenever you end up with Newton's law, you must draw the free body diagram. Okay, so for the mass, so you can have the spring constant like this, spring force. Okay, so then for this, so you will have the spring force acting like this. Okay, so x2, x1 are shown here. Okay, so you can write the equations of motions as okay, for the mass one, you can write m x1 double dot. So this is the net force acting on the system. So this is equivalent to, okay, for the first mass, this is equivalent to k into the difference in the displacement. So the mass 1 is x1, mass 2 is x2. Both are connected. So the displacement here will be x2 minus x1. So this will be your equation 1. Then equation 2 will be m into x2 double dash. So this one you can write it as negative k x2 minus x1. Okay, so these are the equations. So we can write the first equation as m x1 double dot. So minus kx1, if I bring to the other side, it will be plus kx1. So plus kx1 minus kx2 is equal to 0. So this will be rearranging the first equation. So similarly, rearranging the second equation, so we can write m x2 double dot okay. So this is minus k x1. If you bring in the other side, it will be uh, okay, this one becomes minus k x1. Okay, minus k minus x1, it becomes positive. So you bring the other side, it will be negative. So plus kx2 is equal to 0. So this is your rearranging equation 2. Okay, so these two equations we can write in matrix format. Okay, I'll move to the next slide. So we can write in matrix format. So in matrix form, so you can write mass matrix. So from equation 1 and 2, so you can refer the mass matrix will be so M00M. Okay, so the acceleration matrix will be X1 double dot and X2 double dot. Okay, then stiffness matrix will be K minus K. There you have minus K and K. Then the displacement will be X1, X2. So this is a free vibration, therefore no force acting, so 0, 0. So this is how you can write in matrix format. All right. So I think, guys, I use the camera again. So from the matrix format, okay, we can write the solution. So you have similar example, you can go through the similar examples in the learning guide. So we can assume that the x1 and x2, so x1 and x2 can be, we can take it as in matrix format, AB two constants, and we can take the sine omega t plus the phase phi. So we choose the solution in this format. Okay, so substituting this in the matrix format. So basically yields. So you can go through the working in the learning guide, which is given. Okay, so you get negative omega square m plus kx is equal to 0. Okay, so that means uh, omega square. So the matrix is m 0, 0, m. Okay, so the stiffness matrix is k minus k minus k k. Okay, so you can write x1, x2, 0. Okay, so if you simplify this, so you substitute x1, x2 as AB. Okay, so you can get negative m omega square plus k minus k minus k. So you get so this is not a matrix but the determinant. Then AB is equal to 0, 0. So once you simplify the determinant, negative m omega square plus k minus k, then minus k, negative m omega square plus k, a, b should be 0, 0. Okay, so now here you can substitute the values given. Okay, so you can see here the mass is given 2000 kilograms and K is given as 280,000 Newton per meter. Okay, so these values are given. So I noted down the values given m and k. Okay, now substitute these values into the determinant here. So m I replace with 22,000 omega square. So k I replace with 280,000. Okay, minus k is negative 280,000. So minus k is negative 280,000. So minus m omega square. So 2000 omega square plus. So this is determinant multiplied by AB. So is equal to 0, 0. Okay. Solve the determinant. Okay, you get a quadratic equation. Then to find the two frequencies, omega 1 and omega 2. Okay, so now use the frequencies and calculate A and B for omega 1 and A and B for omega 2. Okay, So your job is to find this omega 1, omega 2, then A and B. I think the calculations will take long time, so I just leave it here. Any questions, let me know. So guys, any questions, let me know. So you need to substitute in W1 back into the matrix above. That's correct, Eva. So once you know omega 1, omega 2, you can use this to find out A and B. All right. Any other questions? Okay, how about others? All right, Vinod. So next we move on to question 5. Okay, so the question 5 is again a 2-degree freedom system. Okay, here you are asked to derive the equations of motion. So you are asked to derive the equations of motion for the pitch, that is the angular motion, and the bounce, so that is the vertical motion up and down. Okay. Uh, for a car shown in figure 2, but use Lagrange's equation method. So you are asked to apply Lagrange's method and derive the equations of motion. After that, so determine the pitch and bounce frequencies. So you are asked to calculate the frequencies for these two, pitch and bounce. So based on the derived equations. So you are given that the car body about its mass moment of inertia is given mr squared. Okay, and the required data is given. So all the required data is given. So the free body diagram is you can see the free body diagram for this in the learning guide. So I move on to the learning guide. So you can see the free body diagram here. So the free body diagram for this is shown. All right. So you need to apply the Lagrange's method, not the Newton's method. Okay. So I go back. So you need to write the total kinetic energy. So what is the total kinetic energy? So guys, any answer for the total kinetic energy of the system? So based on the mass and based on the displacement along bounds and based on the angular displacement. So because of the bounds, the velocity will be there. So you can write so total kinetic energy, you can write half m x dot square. So this x represents the bounds. Okay. Plus there is an angular displacement theta. So therefore, there is a rotational kinetic energy. So the rotational kinetic energy is half I omega square. So half, so J naught is the mass moment of inertia. So the mass is replaced with mass moment of inertia. Then the linear displacement x dot is replaced with angular displacement theta. So theta dot is the velocity, angular velocity. Okay, so this is something like half I omega square. So this is the total kinetic energy T. Okay, so similarly, you can write the total potential energy. Okay, so this will be your V. Then write down what is the Lagrangian. L is equal to T minus V. Okay. Nels, any things for the potential energy? So here the system has the springs, both front and rear springs. All right, I think kinetic energy bonds is shared with the two springs. Yes. No, because we are writing the total kinetic energy. So angular displacement is 1. So similarly, the linear displacement or the vertical displacement is only x. So theta is the same for both. So you can consider the entire body as one point mass. Okay, so there is no need to write 2 times uh, kinetic energy. So we treat the entire automobile as a point mass at the center of mass. So the displacement is related to the displacement of the centroid. So the angular displacement is also you can refer back the free body diagram. So theta is only 1. All right. So next, I'll go back to. So here the potential energy can be written as, okay, so T we have written as half mx dot square plus half z naught uh, theta dot square. Okay, so this is the kinetic energy. So potential energy V can be written as, okay. So for the weight of the system, so we can write the potential energy mgh. So this x, we write it as x bar, okay, plus uh, here the potential energy for two different springs, the front spring and the rear spring. So we can write for the front spring kf, okay. So the net displacement, okay, of the spring. So the weight displacement, you take it as x bar. So here the net displacement is x bar into L1 theta bar square. So half k x square. So the displacement is x bar into r theta bar. So this is F represents the front spring. Then similarly for the rear spring, so you can write half kr. So x bar, okay, here this will be plus L2 theta whole square. So here, okay, x bar is equal to, so the actual displacement plus the static deflection. Okay, and theta bar is equal to theta plus the static deflection. So the static deflection is due to weight. Due to weight mg. So now we need to analyze the static deflection and write the Lagrangian. So so you can write in static state. So the weight you can write L1 into theta static So weight can be written like this. Okay, so I'll give you the remaining steps. You can fill up the remaining steps and write down. Okay, you can write L is equal to T minus V. Okay, so you need to do the differentiation. You need to apply the Lagrangian equation for uh, the bounds x. Okay, so where you write for the bounds x the total derivative d by dt of the partial derivative dou L over dou x dot minus dou L over dou x. So similarly for theta, okay, so you can write d, I'm sorry, so d by dt of, okay, so here you are taking the partial derivative with respect to theta dot minus dou L over dou theta. So both cases you take 0. So doing this partial differentiation and simplifying, so you will get equation 1, then you will get equation 2. Now solving these two equations in the same way, you will be able to find out the two frequencies omega 1 and omega 2. Okay, so you can do some research on this problem and try to solve. All right, so I want to differentiate those who can work on these things and yeah, those who do some research and try to answer this question. All right, I stop discussion about this question here. Any questions, guys? If you have any doubts, I can explain. So essentially, you need to write down the Lagrangian, then take the differentiation, apply the Lagrangian equation for x and theta. So then whatever the equations you get, that will be your partial answer. After that, then you need to solve the equations just like the previous example, then derive the two frequencies. Okay, so you can derive the equations of motion, and you're asked to determine the pitch and bounce frequencies. So that means omega 1 and omega 2 based on these two equations. Okay, so just to guide you, so your first equation of motion may be something like this. So your first equation of motion will be mx double dot. So in your assignment, you need to show how you derived this expression. Okay, the stiffness constant for the front AF. So you get x minus L1 theta plus K into x plus L2 theta. So this will be your equation 1. And equation 2 is for angular motion. So mass moment of inertia, theta double dot. Okay, so here this will be negative kf. You get x minus L1 theta into L1 plus kr x plus L2 theta. So this is just to guide you whether your final equations are correct or not. So then based on solving this equation, you will get the two frequencies. All right. So I move on to the next question then. All right. So let us go to the next question. So here the question reads as for the system shown here, where a vertical mass is connected. So this is the vertical mass is connected to a spring. Our midpoint of the slender bar. So this is the midpoint of the bar. The length of the bar is L, mass is M, stiffness constant of this is K. Okay. So now denote the displacement of the vertical mass by X. Okay. And the small rotational angle of the slender bar by theta. So the angular displacement of this is theta. So the mass displacement is X. So all are shown here in the figure. Theta and X are shown. Now, what is given? The mass is given 2 kilograms, the length is given 1 meter, the stiffness constant is given 1 kilonewton per meter. The natural frequencies have been calculated. So in this case, the natural frequencies are given omega 1 and omega 2. So the associate mode shapes are found to be, so x1 and x2, the mode shapes were given for frequencies omega 1 and omega 2. Okay, so now find the free vibration response of the system. So following the initial conditions. So now we need to find the response of the system. The initial conditions are given here. So the initial conditions are the displacement when time 0, t is equal to 0 is 0. The angular displacement when time 0 is 0. The velocity when time 0 is 2 meters per second. So at the time 0, the velocity is 2 meter per second. The angular velocity is 0 when time is 0. So these are the initial conditions given. So now based on this, you need to find out the response of the system. So the response of the system means, so here there are two. One is the angular displacement. You need to find out how much is theta t and how much is xt, the response of the system. So the linear displacement of the system as it varies with respect to time t, and the angular displacement of the system as it varies with respect to time t. So because the initial conditions are given, okay, so we touched upon this in theory. So there will be 4 constants, C1, C2, C3, C4 you need to establish. Okay, so omega 1 given, omega 2 is given, x1, x2, the model shapes given, the initial conditions all given. Okay, so this problem is some things which we discussed in the learning guide. So here omega 1 is given, x1 1, x2 1 is given, omega 2 is given. So we know these things. So after that, okay, I clear these things. Okay, so this is the free vibration response. So the initial conditions are given. So these are the initial conditions. So once you know the initial conditions, then you can apply this formula C1, C2, C3, C4. And once you know these things, then you can substitute back and you can get the required response. Okay, so there's an example here you can see. So this question is very similar to this. So these are the initial conditions. So we have the values. Okay. Then we need to find out this C1, C2, C3, C4. Okay. Then find out the response. Okay. So you can go through this example too later. Okay. So we can write for this particular problem. I go through the camera. Okay, so the initial conditions are given. So given initial conditions, so the displacement is 0 when time is 0. The angular displacement is 0 when time is 0. Then the velocity when time 0 is 2 meter per second. And the angular velocity is 0 also. Okay. So then we have the model shapes. So you can write the general solution of them. So for the response can be written as, so you can write the response will be in terms of the angular displacement and the linear displacement. Okay, so this one you can write C1, the constant. Okay, so the model shapes were given. So this 1 and 1.128 is given. Okay, then we can write cosine omega t. So cosine omega 1t, omega 1 is given. The value given is 16.69 t. Okay, so then you can write plus C2. Then the model shape is given as A1 1.28. So we write both the sine 16.69 t. So we can write in terms of cosine and sine. Okay. Plus C3. Okay, the model shapes for omega 2 given as 1, then negative 0.2949. So these model shapes were given for us. So we are writing the solution as A sine, okay, C1 cos omega t plus C2 sine omega t. Then plus C3, similarly, cos omega 2t. So cos 36.69 t. So plus C4. So 1 negative 0.2949. So sine 36.69 t. Okay. So this is all one equation. So you can call this as equation 1. So in this, we were given this, we were given this, we were given this, we were given this. So what we have writing is, instead of writing A cos omega t plus B sine omega t, so you have the 4, okay? Because we are dealing with 2-degree freedom system, so the responses are 2. So you have 4 constants here. So now we need to find out these 4 constants. Now to solve this particular equation, we know the initial conditions. Okay, when time t is 0, what is the displacement, angular displacement, linear velocity, angular velocity. Okay, so first you can apply the initial conditions. Now if I put x 0 and theta is 0, okay, when t is 0, so when t is 0, this is 0, so this is 0. Okay, So when t is equal to 0, so when t is equal to 0, implies x 0 is 0 and theta 0 is 0. Okay, so what I can write is, now from the equation, I can write 0, 0 here. Okay, I write C1 1.128, then cos 116.69 into 0. So because I'm replacing t with 0, so I get 0, cos 0. So plus C2 1.128 sine 0 plus C3 1 negative 0.2949 cos 0. Then plus C4, so 1 negative 0.2949 sine 0. Okay, so we can write like this. Now cos 0 is how much? So cos 0 is 1, sine 0 is 0. So that means the whole thing will vanish. So the whole thing will vanish. Okay, so you can write, so you can multiply here C1, okay, plus C4, okay, C4 is 0. So C1 plus C3, so C1 into 1 plus C3 into 1, that is equal to 0. All right, so you can write this equation. Okay, next what we can write, C1 into 1.128. So 1.128 C1. Okay, so here C3 into minus 0.2947. So minus 0.2949 C3 is equal to 0. So this is equation 3. Okay, so this is C1, C3. So you have two equations and two unknowns. So you can solve C1 and C3. Okay, so this is when time t is equal to 0. So you end up getting two equations. So similarly, can I take this out? All right, so next what I'm going to do is I substitute when t is equal to 0, that I apply the velocity is 2 and the angular velocity is 0. Okay, then I'll be getting two more equations. Okay, so when t is equal to 0, okay, the velocity is given as 2 meter per second and theta dot 0 is equal to 0. So applying the conditions, in the response equation. So the response equation is theta x dot is 2 meters per second, theta is 0. So you can write 2, 0. So I'm referring to this expression. So I write exactly the same thing, but we need to uh, differentiate this. So cos omega t differentiation will give you because you are dealing with theta dot t and x dot t. Oh, okay. So I think I'll use here 0 theta dot and I'll use here 2. So because theta dot t is 0 and x dot t is 2. Okay. So that means I need to differentiate every term in the equation. So I need to differentiate this, I need to differentiate this, I need to differentiate this. Okay. So if you differentiate cos omega t, you will get minus omega sine omega t. So similarly, sine omega t, if you differentiate, you get omega cos omega t. So write down similarly, okay? So you will be able to find C1, 1.128, okay? So here you get up cos omega t is negative, sine omega t negative, okay, 16.69 sine 16.69 t. Okay, so plus C2 into the same thing. Okay, so 16.69 into cos omega t, 16.69 t. Then plus C3 into, so I'm just ignoring to write the same things. So cos omega t is minus 36.69 to sine 36.69 t. Then plus C4 into, so this one becomes 36.69 t sine omega t becomes cos omega t. So cos 36.69 t. Okay. So now substitute t is equal to 0 in all the equations. Okay, in all the places. So sine 0 becomes 0 again, cos 0 becomes 1. Okay, so you end up getting two more equations. Okay, so you get two more equations. Write down those two equations. Okay, so we numbered 2 and 3. So write down equation 4 and 5. So substituting t is equal to 0. So solving equations 2, 3, 4, and 5. Okay, so you can find C1, C2, C3, C4 values can be calculated. So once you get C1, C2, C3, C4 values, so just substitute the values, so that will be your response. So substitute the C1, C2, C3 values, so you will get the response. Uh, Guys, is that clear? Do you have any questions? I'm stopping the recording. Yeah. Let me know any questions, guys. Need to digest. Yeah, it takes some amount of time, definitely. Because in 4 hours we are discussing too many things, so it takes time. That is very valid. But mechanical vibrations, you have a lot of mathematical questions, mathematics related. But exams will be bit more easier compared to the solid mechanics. Because solid mechanics is many more calculations, and once you complete all the topics, there will be more confusion. But in vibrations, this is the last topic, and so normally you get uh, two questions from multi-degree freedoms and four questions from single degree freedom. So the type of questions will be very similar to your assignment questions. So uh, exam will be easier for vibrations. All right, any questions, guys? So we are left with one more session. So in the next session, I'll be able to go through your class test related stuff, and also we can touch upon the next assignment. Yeah, and also I'll just give you some idea about the end of term exam. And yeah, after that you will have the pre-exam workshop. So uh, that Fahd will be, he's a very experienced researcher, so he'll be able to provide you more insights into the vibrations. All right, any questions, guys? Why don't you use your mic if you have questions? I'll stop here. Wait for your response or any questions.